right, these notes are going to be on graphs and tables of inverses. So we're going to start off with an example of equations. So we have the function y equals 2 times x minus 1 to the third plus 4. And if I think through what's happening to the original problem, I'm starting with a number, and then from that number I'm going to subtract 1. So we're starting with x, and then we subtract 1. And when I get that result, I'm going to cube it. So that's x minus 1 cubed. And then I'm going to multiply by 2. So that is x minus 1 cubed multiplied by 2. And then last, I'm going to add 4, and that's how I get my result. So x minus 1 cubed times 2, and then plus 4. So if I start with the number x, then I could say like x equals 2. 2 minus 1 is 1. 1 cubed is still 1. 2 times 1 is 2. 2 plus 4 is 6. So I started with my number, I subtracted 1 and I got 1. I cubed that number and I got 1. I multiplied it by 2 and I got 2, and then I added 4 and that gave me 6. So for the original problem, if I plug in 2, I get 6 as a result. Okay, so that means for the inverse, we're going to go backwards. So we're going to start with a number, then we're going to subtract 4. So starting with a number, then we're going to subtract 4, divide by 2. So x minus 4 over 2. Then we're going to cube root, because we're undoing cube it. So now we have the cube root of x minus 4 over 2. And then last, we're going to add 1. Okay, so to check and make sure that the inverse works, I'm going to take this result and I'm going to start that. So I take the number, I subtract 4 and I get 2. I divide by 2 and I get 1. I cube root 1, and it's so when I'm saying what multiplied by itself 3 times is 1, and the answer is 1. And then I add 1 to it and I get 2 as the result. So this is saying, I started off with x equals 6, but if I plug in 6, I get 2 as a result, and you see that this relationship is exactly what we would expect of inverses, that the x and the y is traded. Right? So if we want to graph this, then we're going to go ahead and we're going to start by plugging it into our calculator and getting the table values. So I have 2 times x minus 1 to the third plus 4. And if you guys recall, I always want to look at the graph and I want to see where the vertex or where the locator point is. And I kind of want that to be like the middle. So my locator point is 1, 4. So when I look at the graph, I'm going to look for 1, 4, and I want that to be kind of my middle. Okay, so for the original problem, I'll make it the middle. I have the point 1, 4, and then I've got 0, 2, and -1, -12. 0, 2, -1, -12. And then I have 2, 6, and 320. 2, 6, and 320. So that's the original. And then that means that for my inverse, all I need to do is I need to flip all those x and y coordinates. So -12, -1, 2, 0, 4, 1, 6, 2, 23. And then I can graph all the original points and have the original, and I graph all the flipped versions, and then I have the inverse. So I'm going to go ahead and find some of this information. I'm going to sketch the graph, so it's not going to be perfect. So I need to be able to go to 12, 6. So I have left 1 down to 12, which is off the paper, but we'll pretend that we got it. 0, 2. Did I write that down? Negative 1, negative 12, no, 0, 2. 1, 4. 2, 4. And then 2, 6. And so I know this is one of those cubic graphs, so I know it looks something like that. It's not perfect, but it's okay. And then I have left 12 down 1, 2, 0, 4, 1, and 6, 2. So I can see. Now, if you guys can see this, it's almost like we reflected the graph over this diagonal line in between. And that's because when we graph the original problem, this is y and its inverse, y inverse, they're actually reflected over the line y equals x. So we're going to say inverses are reflected over y equals x. Okay, so there's some information you can actually see about this graph. Like here for the original, 0, 2 is a y-intercept, but for the inverse, the point 2, 0 is an x-intercept. So anything that crosses the y-axis on the original crosses the x-axis on the inverse. If I want to go ahead and take this graph right here and figure out what the y-intercept is of the original function. Oh, sorry, the x-intercept. I already knew the y-intercept. So the x-intercept, I'll do my left bound and my right bound. The x-intercept is negative 0.2599, which would be negative 0.260. So for this one, I'm going to go ahead and add it down here. My x-intercept is negative 0.260, 0. So that means for this one, my y-intercept, if I trade those values, would be 0, negative 0.260. So the x's and the y's always trade. That's kind of the interesting thing that we need to remember. All right, so let's say I gave you a problem. And this is going to call this, this is not a function, this is a relation. And it just gives you a bunch of points, like 3, negative 6, 7, 7, 8, negative 11, 2, 16, negative 4. If you wanted to find the inverse of this, then you would say f inverse, and all you have to do is trade all the x and y coordinates. You don't do anything funky, you don't change the positives and negatives, you just trade them, and you're done. And so that's all we're going to be working on, is we're going to have some values for relations. We might have a graph that I'm going to ask you to pick points off of and then change them and draw the new graph, or we might have a table and then find the new table. All right, so that's all we're going to focus on in class, is finding the inverse, but not necessarily focusing on an equation, focusing more on points that you were given, or a table that you were given, or a graph that you were given.